Here we're going to talk about exceptions to the octet rule. So there's incomplete octets, odd number of electrons on the rare chance that you get that, and then expanded octets. So some exceptions, incomplete octets, we have some compounds where the total number of electrons surrounding that central atom needs to be fewer than 8. So beryllium is an example where it needs just 4. You're already familiar with hydrogen and helium, which need 2. It's called a duet. And then group 3A often is okay with just 6 valence electrons. So boron and aluminum are commonly just 6. Boron especially, very, very common that it would only have 6 valence electrons. So these would be the better Lewis dot structures for these compounds here. We're not going to deal with it too much, but if you have an odd number of electrons, we do have some molecules that contain an odd number of electrons. We have not encountered that very much. And because of this, that means the central atom will often not have, it won't have 8 because of you have an odd number of electrons. These are often referred to as free radicals, where you have just one lone electron, not a lone pair, but just a single electron on an atom. These are highly reactive in general. It's because that they tend to want to be paired to form some sort of covalent bond with an unpaired electron from another molecule. And we're maybe somewhat familiar with free radicals and understanding that those are chemically reactive species. So here's an example of one of these free radical sort of situations. ClO2. So oxygen's on the outside. There's 2 of them versus 1 chlorine. So we'll start with something like this. We have 7 valence electrons for chlorine, and we have 2 oxygens, both that have 6. Okay, so we're going to get 19 valence electrons. Most of the time, for my purposes, if you ever get 19 valence electrons, it's likely that you forgot the charge. That's a common issue. If you're confident that you have an odd number, it means that you're going to have a radical, which is again, something that's fairly abnormal. So we'll do our normal sort of setup. We'll fill our octet of our outermost atoms first. Okay, so now I've used 8 plus another 8, so we've used 16, so we have 3 left, and I just start adding those to the central atom. So now you can see I have this one lone electron on the chlorine plus a lone pair. And this would be a radical situation. Like I said, a radical, it's odd because, or it's radical because we have an odd number of electrons. Yeah, so this would be an example of one of those radical situations. We also have expanded octets, and this happens very, very frequently. Atoms of the second period elements cannot have more than 8 valence electrons around them. So this encompasses carbon, nitrogen, oxygen, fluorine. And those are very common atoms, right? Carbon, the basis of life, oxygen and nitrogen, very common atoms that we're dealing with. Those must obey the octet rule. But once you get big enough, they can fairly easily break the octet rule. They're not going to do it all the time, not under all circumstances, but if there's a reason for them to break the octet rule, they will. So once you get to the 3s and 3p orbitals, elements in the third row, they actually do have 3d orbitals available to them. It doesn't mean that they have electrons in those 3d orbitals, right? Like let's say sulfur. If you take a look at sulfur, its valence electrons are the 3p electrons. What it's saying is it's close enough in energy to 3d electrons that actually, if it needed to, it could expand its octet beyond just the 3s2, 3p6. So that's because of that, anything beyond essentially carbon, nitrogen, oxygen, fluorine, neon, anything beyond that, we have the ability now to expand the octet. And sulfur and phosphorus are going to be common examples of something that will expand the octet. So here you have sulfur hexafluoride. In order for sulfur to have 6 fluorines around it, it must have more than 8 valence electrons. Here it has 6 bonds, so it has 12 valence electrons, and that ends up being totally fine. Kind of as a side note, a side example here, we had talked about ClO2 on the prior slide. We also have, and you're very uncommonly going to see, like I said, radical, but we do have ClO2 minus, which is chlorite, and that is a polyatomic ion that we might be familiar with. This has 20 valence electrons. So we can take a look. Let's, just make our same sort of setup that we did before. Form some Lewis dot structures for ClO. This is a negative charge on it now, right? So I'm going to need to use parentheses and minus charge. And here, we're going to fill the octet of everything. Once we get to here, we still have 4 more electrons. So we'll put both of those lone pairs on the central chlorine. And this seems to be doing just fine, right? I would actually propose that there's an alternative Lewis dot structure that seems, there's a resonance structure here, a Lewis dot structure here that that also could be viable. And there's one more with the using the other oxygen. But what if I took one of these oxygens lone pairs and turned it into a bonding pair? I've now created 10 valence electrons around that chlorine. So I'm breaking the octet for the chlorine. But there may be a reason for me to do this. If we take a look at, remember, formal charges help dictate for us which Lewis dot structure is more preferable. So if we take the valence electrons of each of these, so there's 6, 7, 6, 6, 7, 6. Okay, let's do minus the 1/2 the bonding electrons. So this is minus 1 bond. Here we have minus 2 bonds, minus 1 bond. Oxygen, minus 1 bond. Minus 3 bonds here. Oh, sorry about that. I don't know what happened there. All right, so minus 3 bonds. And minus 2 bonds. Now minus the lone pair electrons. So here I have 6 electrons. Here I have 4 electrons. Again, 6 electrons. Here, minus 6. Minus, I suppose I'll put in my minuses for everything. Minus 4. And minus 4. So if we take a look at formal charges, oxygen has -1 here, +1 for the carb or the chlorine, and then a -1. This adds up to -1, which was needed for this to be a valid Lewis dot structure. So that does add up to -1. And now let's take a look at this one here. The oxygen's -1. The chlorine and these other oxygen are 0, however. So this actually might be a better representation, or is a better representation of ClO2 minus chlorite, that 20 electron system. And we're actually violating the octet rule of the chlorine in the middle there. And that's in order to get a more favorable lower magnitude values of these formal charges. Okay, so kind of a notable example, and there's plenty of examples just like this, but you have to have some reason to violate that octet rule. Generally, it's still preferred to obey the octet rule if you can, but there's going to be times like this where maybe it is preferable to expand that octet. And again, chlorine can. It is a part of. It's the 3p electron. It is certainly big enough to start violating the octet rule. So here it is. So let's try some of these. Draw the Lewis structure for boron triiodide, arsenic pentafluoride, xenon tetrafluoride. All right. So boron triiodide. Here. we'll add in all of our atoms. Okay, and we have 3 times 7 for the iodines, so that should be 21, plus boron, which has 3, so we should have 24 valence electrons there. We'll fill in our outermost atoms octet first. These are the most electronegative. And now we've used all 24 electrons. And boron does not have a filled octet, but remember boron prefers 6 valence electrons. So this is actually totally fine just the way it is. So this is an incomplete octet, and it's preferred this way for boron. And again, you can see aluminum doing the same thing on occasion. So, okay, let's take a look at arsenic pentafluoride. Just as right from the get-go, we know that arsenic is violating the octet rule because it has 5. It has to have 5 bonds to it, so that's already 10 electrons associated with it. But we have to see if it has any more. It could have another lone pair, for example, or something like that. It's not going to have any double bonds because fluorine can't break its octet here. So, all right, so we do all of this. We wanted to figure out how many valence electrons we had. So I'm getting a little ahead of myself here, but arsenic, if you take a look at arsenic on the periodic table, arsenic is a 4s2, 3d10, 4p3. So if you just look at the 4s2, 4p3, that has 5 valence electrons associated with arsenic. So that's why it's going to have 5 bonds, and each one of fluorine wants 1 bond as well. So if you were to count up the electrons, this is how many electrons that you would expect to get if you were to do that. So it's at 40 electrons here. Okay. All right. Xenon tetrafluoride. Okay. So xenon isn't automatically breaking the octet here because it only has 4 bonds, which is a good start. All right, hey, it did it again. All right, so how many valence electrons do we have for, so fluorine is going to have 7, and there are 4 of those, right? So we have 4 times 7 gets us 28, plus 8. Should get us 36 electrons. Okay, and then we'll start filling in the octets of the fluorines like we had done. Once we do all of this, we will have used 8 electrons from each of the fluorines total, because that including those bonds. So we're going to get to just 32 electrons that we've used so far. Okay. So now we have 4 extra electrons. Those extra electrons have to go on that central xenon, and xenon can break its octet. So we're going to put a lone pair, 2 lone pairs on the xenon, which is a total of those 4 extra electrons. So those are now gone. And this is the Lewis dot structure for xenon. So xenon has 2 lone pairs on it plus the 4 fluorines. So xenon is breaking its octet to get up to 12 valence electrons. And again, xenon is plenty large to be able to deal with that. Xenon is massive, so it's fairly common that you would experience this for something like xenon, plenty big enough to expand its octet.